Okay, imagine stepping into the Colosseum of Cambridge exams. Only the prepared survive, right? And today we are equipping you with the absolute ultimate armor. If you're targeting top marks in Cambridge IGCSE Additional Mathematics, syllabus code 0606, you are in the exact right place. This explainer is going to focus on a very specific, highly tested battlefield, finding the equations of tangents to a circle entirely without using calculus. This is a pure, unadulterated test of your algebraic and geometric mastery. We're going to break down exactly how examiners grade your work, how to structure your answers logically, and most importantly, how to avoid the deadly traps that catch literally thousands of students every single year.
Look at what a senior examiner recently pointed out. They said, mastering solving problems involving tangents to a circle is essential. This topic appears in every examination series. I really cannot overstate the stakes here. This isn't just a topic that might show up if you're unlucky. It is absolutely guaranteed to be in your exam paper. So investing your time into mastering this specific skill, it's not just good practice, it's a critical mathematical survival strategy. If you know exactly what the examiners are hunting for, you can essentially secure these marks before you even walk through the doors of the exam hall.
All right, let's dive into Section 1, the Exam Blueprint, Core Theoretical Principles.
To truly conquer these questions, we really need to understand the difference between your average student and a top-tier candidate. It comes down to analytical depth versus superficial breadth. You know those answers where someone just overloads the page with raw math facts? They throw down the circle equation, maybe a generic linear equation, but there is absolutely zero logical flow between them? That's superficial breadth. Now contrast that with an answer that carefully tracks the specific command words in the prompt, building a tight, step-by-step argument. The examiners are explicitly prioritizing candidates who can demonstrate deep, logical reasoning. They are not looking for someone who just memorizes and regurgitates formulas.
So, there are actually 3 cognitive domains the examiners are actively targeting when grading your papers. Think of it as a hierarchy. First, knowledge and understanding. When you're asked to find the equation of a tangent without calculus, you must first show you know the basic geometry, like clearly demonstrating that a tangent is perpendicular to the radius at the point of contact. Then comes application. This is where you actually use the negative reciprocal of that radius gradient to find your tangent's gradient. And finally, analysis. This is the top tier, requiring you to synthesize all these individual geometric and algebraic pieces into a final, highly precise linear equation.
What this means is your theoretical architecture has to rest on 3 specific pillars: precise definitions, causal relationships, and cross-topic connections. That last one is huge. Principal examiner reports continually highlight that candidates who reference cross-topic connections achieve significantly higher marks. For tangents to a circle, this means seamlessly blending coordinate geometry, like finding the gradient and midpoint, with pure algebra. A classic example? Using the discriminant. Setting b squared minus 4ac equal to 0 is exactly how you algebraically prove a line touches a circle at exactly one point. Integrating these distinct math topics really is your golden ticket to those highest grade boundaries.
Okay, moving right along to Section 2, Technical Methodology. Let's look at the procedural framework.
This is your battle plan. It's an exact 5-step procedural framework that practically acts as the examiner's grading rubric. Step 1, identify key elements. Extract the center of the circle and the radius from the given equation. Step 2, apply relevant principles. If you're going the geometric route, firmly establish that the tangent is perpendicular to the radius. Step 3, execute analysis with clear working. Calculate the gradient of the normal, find that perpendicular gradient, and substitute your coordinates. Or, if you're using the algebraic method, substitute the line equation into the circle equation and set that discriminant to 0. Step 4 is verifying your results. And step 5 is presenting in the appropriate format, usually y equals mx plus c, or maybe ax plus by plus c equals 0. You need to memorize this sequence. Now, there are strict conventions for presenting your math, and no, professional formatting isn't just to make the paper look pretty. It literally secures your practical application marks. Using the correct terminology, writing discriminant instead of just vague phrasing, and clearly annotating your steps so the examiner can actually follow your logic is vital. Also, providing the final answer in the exact format requested by the command word. If the question asks for integers a, b, and c, and you leave your final equation full of fractions, you are dropping super easy marks. It's all about showing professional, structured skills.
Let's jump into Section 3, Evaluation and Examiner Insights. These are some critical warnings you need to hear.
I want you to burn this concept into your mind. +1, the method mark. This is, without a doubt, the single most important point you can earn on any line of your working out. In the Cambridge marking scheme,
An M1 mark means you get credit for knowing how to solve the problem, even if your basic arithmetic totally fails you later on. It's your ultimate safety net in the arena. It will catch you if a simple addition error tries to drag down your entire score.
Which brings us to a massive examiner alert. Please hear me on this. It's a warning straight from the marking rooms. Students consistently lose marks by not showing their working. Imagine doing all that complex algebraic substitution in your head or scribbling it on some scrap paper, making one tiny little negative sign error and scoring a literal 0 for a 5-mark question. It hurts just thinking about it. If you simply write down the discriminant equation clearly and substitute your variables on the page, you secure those vital method marks. The process is just as important as the final answer. You can let your red pen mistakes transform into green check marks simply by showing your logical path.
Let's look at the actual data here. The top 3 traps identified in principal examiner reports for these 0606 tangent questions are super revealing. 34% of students lose marks for using the wrong approach for the context, like trying to use calculus when the syllabus explicitly demands algebraic or geometric methods. 33% forget format and presentation, just leaving their equations unsimplified. And another 33% give answers not specific to the context, like finding 2 equations when the question clearly specified the tangent with a positive gradient.
So how do you push a good grade into an exceptional one? You evaluate the mathematical realities of your working. You need to identify limitations and recognize any assumptions you're making. Think about it. Does your chosen method only work if the coordinate given is actually on the circumference of the circle rather than some external point? Are you assuming a line intersects twice when your discriminant math shows it only intersects once? Noting these different interpretations and evaluating how they affect your final conclusion is next-level stuff. Even a quick visual sketch of the gradient can immediately verify if your calculated answer makes geometric sense.
When interpreting complex data in additional math, execution requires rigorous analysis of your geometric shapes and their relationships. If a question throws 2 circles at you or a circle and a secant line, you have to systematically extract the correct data and interpret those relationships. For instance, if you calculate that 2 tangents are parallel, analyzing their discriminants in relation to the circle is what proves they yield the same gradient but different y-intercepts. Drawing those clear, solid, evidence-based conclusions from your algebraic working, that is exactly the level of execution examiners are dreaming of seeing.
So we're going to end this explainer with a bit of a provocative challenge for you. Go grab your last past paper and look at it objectively. Will your working out actually secure the method marks? If a Cambridge examiner looks at your page, are they going to see a logical, step-by-step masterclass in coordinate geometry and algebra, or are they going to see a chaotic scramble of numbers? Because the difference between an average score and absolute top marks lies entirely in the clarity of your process. Keep analyzing, keep practicing those foundational principles, and you'll crush it. We'll see you in the next explainer.